Well, welcome everyone to our second in a series of three broadcasts on electromagnetic effects. My name's John Twardock. I will be your host today. We're going to be continuing our discussion with Dr. Tim McDonald, President of EMA. During our first session, Tim and I explored some of the basic principles of electromagnetic interference and compatibility. And we also walked through the evolution of various methods and tools to predict EMI and ensure electromagnetic compatibility. But today we're going to dive a little bit deeper into state-of-the-art approach for simulating EMI and EMC effects. So welcome back, Tim. I really appreciate you taking the time to speak with me today.
It's great to be back, John.
Well, thank you. So we're going to talk specifically about the EMA3D Cable software, which is described as a platform-level EMC cable modeling solution. Can you explain more about what is meant by the term platform-level electromagnetic compatibility solution?
Absolutely, John. So when we're modeling for electromagnetic compatibility, and in the real world, when we test those products for their performance, we tend to do so at the platform level or the enclosure level. Meaning, if I have a car that has to pass electromagnetic compatibility testing, at some point by regulation, I have to test the whole car. Or if I'm testing a computer or a consumer electronics device for electromagnetic compatibility, at some point I have to take the entire device, take it to an electromagnetic compatibility chamber, and have it measured. So if our goal is to use simulation to design products that will pass the first time when we go into that regulatory testing, then we need to simulate like we test. And that means to include the entire enclosure, the entire cable, or all of the cables that go with that enclosure, the entire platform, and the cables that go with that platform. So that's really what we're talking about when we say this is a platform modeling tool.
Oh, excellent. Well, thank you for that explanation. So you mentioned then that the companies have to go in for EMC or compatibility testing. Do you have an idea of how difficult it is? How many of them fail? What percentage, for example, fail on their first attempt?
Yeah, it really depends by industry and application and how much design work has gone ahead of time. But we had one of our key customers look at some of their metrics, and they found that they were failing their initial EMC testing about 50% of the time. And they looked at the statistics further and found that approximately 30% of their units were failing multiple times. So you can imagine when the test chambers book out months ahead of time and passing the test is required to start selling your product, having delays like that late in the program can be a huge headache. So having something fail not once but multiple times, that can be a huge cost and really destroy a product launch.
So let me make sure I understand correctly. The end result or the consequence of failure is they cannot ship their product?
Absolutely. So there's sometimes that we do electromagnetic compatibility just for product performance. For example, anyone using a consumer electronics device does not want that device to stop working just because you walk by a cell tower. There's other times that the compatibility is required by regulation. So for example, in a car, any safety critical function is required to pass EMC by regulation. So that means the government tells you for your automatic braking that many new cars now have, if you don't pass EMC and on that automatic braking system, you have to just take the cars off the assembly line and put them in a parking lot until you come up with a way to retrofit those already manufactured vehicles to solve the problem.
So you've mentioned a couple of industries already. You mentioned automotive, electronics. Is this certification popular or common across many industries?
Essentially, every electronic device will at least have to have Federal Communication or FCC regulatory compliance in the United States, and every country has their own equivalent. And that's just ensuring that devices are not emitting in such ways that they interfere with spectrum that we're using for things like cell phone communication or emergency bands, things like that. So think about that. every electronic device has to pass some form of EMC. And certainly as our devices become smarter, it's rare to buy a new product that is not somehow connected to the internet, somehow connected to Wi-Fi or cell towers. So that means if you look around your office or you look around wherever you're listening to this broadcast, probably everything you're looking at had to pass some form of EMC compliance and was forced to do so by regulation.
So this is definitely not optional. And because it's not optional, I'm curious how expensive and how time consuming. I mean, I know there isn't one number, but maybe give me a range for how costly and time consuming would it be to do this?
Sure. The tests themselves are not terribly expensive. They're a few $1,000s per day in the test lab. Certainly getting time in a test lab is a big deal, but the cost does not come in the testing itself. That's not what we're talking about in terms of savings. The cost is really in delaying your product launch. EMC testing is typically done as the very last thing as we develop a product. And that's by design. We want to do it after we do vibration testing, thermal testing, because we want to see if we knocked anything loose that will impact EMC. But because EMC is last in the cycle, that means you've already ramped up production of your product. So if you discover you have an EMC failure that requires you to go redesign your product, respin boards, redesign the cable system, and you're already in production, the cost to you as a product developer, a product integrator is maybe 100 or 1,000 times greater than if you made that design change at the beginning of your program. So as we decide how much cost we're saving using analysis tools, we need to consider the opportunity cost or the risk of having a failure that happens so late and forces you to start from scratch on a product launch.
So it really speaks to the overall value that many of us know about simulation, which is just doing it up front before you commit to a lot in production and you're too far down in the design process. I want to drill in again a little bit more on the entire platform, or maybe pose my question a little differently. Why couldn't you just model the components individually and get an adequate solution for compatibility?
Sure. Well, the first answer to that is that the platform itself is going to affect the emissions of what's in it. So if we're talking about an electronic device, we could have a board inside the device that is very noisy. And if it's inside of an enclosure that provides some shielding, if the cabling to that device is well shielded, then maybe that emission's not so much of a big deal. There's other cases where you may have a board or you may have signals driving on a cable that are not large in magnitude. There may be moderate signals. However, if the enclosure is very leaky and the cables are not well shielded or not balanced, you may have an interference problem. So the pass and fail for electromagnetic compatibility is intimately intertwined with the entire product design. It is a function of course, of the PCBs and the packages and the electronics, but it's also a function of the device itself and a function of the cables and the shielding on those cables.
So the whole electronic system is really one ecosystem of electromagnetic effects that you have to be concerned about. How large of a model can you do then with the simulation software? Is there some size or complexity limit?
Yes, let me show an example of some large platforms that we might typically model. So this is a large high performance aircraft. You can see that it includes the exterior details, but it also includes the interior details. And finally, it has a representation of cables connected to equipment. So those cables, if we take a look, they're represented as individual conductors within a harness. We could add shields to this harness. We could make adjustments to how many conductors are in that harness. But you can see all of the interior components, all the exterior components are included in the model. And everything we see here in this simulation are CAD derived from the mechanical CAD. So all of this can be brought in and integrated with our electronic aspects of our product design to have an overall comprehensive representation of its electromagnetic effects. We include the details of the platform, the details of the PCBs, the details of the cables, and the product integrates all of that together so that we can see all of those effects all at once.
Well, that's a very detailed, complex model. Is that what's the kind of largest model that your team has run? Is it a full aircraft like that?
So certainly it's common for us in the last 40 years to simulate full aircraft. And in fact, most aircraft are required to meet lightning and other types of electromagnetic compatibility, such as with ground radar systems and radio towers. And in the United States, the Federal Aviation Administration is in charge of certification of aircraft. And that work has evolved hand in hand with simulation technology, such that at this point it would be impractical or maybe impossible to get certification of a transport category aircraft without the use of full wave simulation like EMA3D. So the processes to prove that an aircraft are safe are intimately intertwined with that simulation. And so it's very routine for our team to do entire aircraft models of all the cables and all of the electronic devices installed on that aircraft.
That's significant complexity, Tim. I'm curious, do the results show what's happening inside the fuselage only, or do you get a view of how much is leaking and what's happening in the exterior of the aircraft?
One challenge of electromagnetic effects is we have to consider what happens in the environment, the lightning, the fields from radars that interact with the aircraft. But we also have to be concerned about what couples to the inside. So there's structures, bulkheads inside the aircraft, there's cable harnesses, there's electronic enclosures surrounding those electronics. We need to consider all of those effects or we can't get the right answer. So that's a big challenge for integrators, and that essentially forces us to use tools that allow us to include all of that complexity without blowing up the effort. If the effort took too many man hours, game over, this doesn't work. It's really all about coming up with a way to include all of that complexity in an engineering representation that can be added in a practical means.
So you're really doing both inside and outside, for sure.
That's right.
So in our first session, we talked a little bit about some of the other tools that are available to do electromagnetic simulation, and two that came up are Ansys HFSS and Ansys SI Wave. How are those tools different from EMA3D Cable?
Certainly. So SI Wave is a very useful tool when modeling PCBs and packages. It's a purpose-built tool, and it can give us some design checks, including electromagnetic compatibility and electromagnetic interference design checks. You can import a board and you can learn quickly if you've violated some standard design rules. You can even calculate the fields emanating from that board. That's fantastic, but that product does not consider modeling of enclosures and cables and platforms. So we've added workflows with SI Wave to pull in the fields from SI Wave to complete the problem so we can model not just the boards, but also include the details of the full platforms. And HFSS is the gold standard for accuracy. It is an extremely versatile tool that models electromagnetics, small things, large things. It's about extreme accuracy, and engineers around the world trust HFSS and rely on HFSS. And in fact, I use HFSS, my team does as well. There are times though when the platform or the enclosure complexity makes it time prohibitive to use HFSS for all the parts of that product. So we like to use the right tool for the right job. If we're modeling packages, if we're modeling antennas, we are using HFSS. And in many cases, we may grab the fields and bring that in as a field source and use EMA3D for modeling the aspects of the cables, the platform, and other coupling aspects where we want to use EMA3D where it does a good job capturing the level of accuracy we need on the type of complex geometry we need. And we use HFSS where we need to use HFSS for those components where we need that extreme accuracy.
So if I understand then, HFSS and SI wave, they're most appropriate for very detailed simulation of emissions from individual components like PC boards. That's correct. And then if you've done that simulation, then you can leverage that result as input into EMA3D cable.
That's correct. And we've made that workflow very straightforward where you can pull in those fields with one click, reposition the component that you've created, and then model your overall platform.
Well, another issue with simulation, and I'm certainly aware of, is just the long-standing issue of getting the geometry to be usable for a model. You have to bring it in, import it, you clean it, you repair it, and then finally get it into a usable mesh. And I would think the electrical engineering field, they're not as familiar with doing that as, excuse me, as the mechanical engineering guys are. So how does EMA3D address that? Because that's a big time-consuming problem.
Yeah, EMA3D takes the mechanical part of our simulation head on, and we organize all of our 3D simulation around that mechanical CAD. So that means you can bring in the mechanical CAD. We have a very forgiving computational mesh technique that's based on a voxel grid. Now we have a multitude of features to correct for the artifacts introduced by the gridding on that regular Cartesian grid, and to allow for simulation of features that are smaller than that grid size. So by using those subscale features with the voxel grid, which is a very forgiving technique, we can mesh that mechanical geometry with zero requirements for cleaning and preparation. So that means what you would think of for a full vehicle platform, you would say, well, that's going to be a few weeks or months of cleaning and prep just in the geometry to run the first sim. In EMA3D, we can start running that first simulation right away, immediately based on that imported geometry. So we can focus on our product design, our product EM performance. We don't have to spend that time worrying about the geometry preparation.
So I think some of our listeners are probably not that familiar with a voxel mesh. Can you compare and contrast that to a finite element mesh, and maybe why you use the approach? I think I have a little understanding now of why you use the approach, but I'm curious as to how you'd compare the two.
Sure. With a finite element mesh, you're creating mesh shapes that can be conformed to a wide range of geometry, and they're volumetric elements. And so there are smaller elements in some areas and larger elements in others. There's quite a bit of technology and work that has gone into making that work across a wide range of length scales and variations in the resolution needed. Whereas with the voxel grid, takes a different approach. You're capturing the voxels, create essentially a voxel. Think of it as like a 3D pixel. It's like Minecraft, but generally with smaller boxes. Those boxes represent the volumetric parts of geometry. And then for the surfaces, there's work that goes into modeling how the surface tessellations, which actually conform to the actual geometry, overlays that voxel grid, or lines and seams and one-dimensional elements, how they lay across those voxel grid. And there's corrections that are utilized to use that voxel grid to model things that may themselves not be on that voxel grid. So using a combination of smaller voxel sizes or these subcell features, you can build up models that are accurate for a full platform. The advantage, the reason to choose that, it's all about the workflow. The engineering effort, the manpower to build the models based on the voxel grid are huge. You save a lot of time. You save also some time in the simulation time. So it's a trade-off that engineers consciously make, picking the right tool for the right job, the right thing.
Well, it sounds like it's a much faster technique for meshing, certainly, and that's great. But as an engineer, I'm going to want to know, is the price of that speed and convenience, is it reduced accuracy? I mean, is the approach accurate, and do you have examples to back that up?
Sure. So we've been using the volumetric voxel techniques in some form for around 40 years. And on large platforms and complete devices, we've been able to show and have published in the literature examples of simulation compared to experimental measurements. So it takes a lot to get good validation, regardless of your technique. You've got to understand the properties of what you're modeling. You've got to represent it properly. But with the voxel and the subcell modeling techniques, if you use them the right way, they can build accurate models for electromagnetics, electromagnetic compatibility, lightning HRF, and desense problems. They can be accurate, and they can save significant amounts of time. And finally, they can model things that would be, frankly, just impossible with other methods, just because of the complexity of a full aircraft.
Well, it sounds to me like EMA's done a nice job tackling the whole geometry phase for simulation of electromagnetics. So let's talk about the solvers a little bit, because I read that EMA uses a co-solving approach. So what are the various solvers that EMA3D Cable uses, and how do they work together?
Certainly, that's a great question. So let me show, we've got 3 different solvers that are working together to solve the coupling problems that we typically solve. The first is the 3D structures. The structure of the aircraft are solving using that voxel finite difference time domain technique that I described. So we're solving Maxwell's equations on that grid, self-consistent with several subcell modeling features. But the most important subcell modeling feature, and really our claim to fame as a product, is how we model cables. So the cables exist in both worlds. They live in the 3D model, and they're represented as this line that flows through space. But those cables also are represented by their cross section. And so we're using transmission line theory. So we're doing a capacitance and inductance matrix electrostatic solve, and then we're taking advantage of the telegrapher's equations to solve down the line. And this is heavily modified multi-conductor transmission line theory to handle shields, to handle multiple conductors, branches, conductors breaking out of shields. All of the things that are not really possible in traditional transmission line theory are made possible with this hybrid simulation. So we get the best features of transmission line theory. It's extremely efficient simulation and extremely efficient model setup. And we combine that with the accuracy of the full wave 3D solver. But it goes even further than that. We have recently added the ability to co-solve a third solver using the Ansys Nexum transient solver. So we can add an arbitrary circuit schematic to the end of any of the cables to represent the electronics. So by using those 3 solvers together, anything that you can throw at us in terms of a coupling problem, we can solve in EMA3D with those 3 techniques working together.
That multi-conductor transmission line solver, to me, that sounds like a bit of a game changer. I can personally imagine how difficult and comparable it would be to do a finite element model of a cable with multiple conductors inside. That's just going to be very impractical and a fairly large model. How much faster does it run compared to finite elements? I mean, is it a faster solve technique with 3 things solving simultaneously?
Sure. So the transmission line theory, because we get the electrostatic solve out of the way first, the remaining part of the transmission line theory is a one-dimensional solve down the line. And that solution is being solved self-consistent with the 3D equations at every step down that line. And so actually that transmission line solver is so efficient, it's a very small change to the timing of the 3D model. And the same way the circuit model is a small change to those other 2 models. So the efficiency is driven by the full wave component. So we put the hardest part of a of an EMC problem into the transmission line theory, essentially. If you imagine a car, there's so many conductors in a modern car. Think about the infotainment system, all of the controls, just the adjustment for my seat positioning. There's multiple harnesses, multiple conductors in that harness. All of the devices we use have so many cables, and those cables have things like weaved shields that are made out of braided filaments. Some of those filaments are usually smaller than a millimeter. So I think no CAD platform in the world is representing those tiny braid filaments. It's just not practical. It's not possible. You would start now, and maybe in 10 or 20 years, you could build a model with those tiny braid elements of a cable. It's really important that we use an efficient representation for full product electromagnetics, or game over. You can't even come to the table because it takes too long to build the geometry.
Well, let's drill in a little more on the electrical signals. How do users get them into the model? I mean, this is like boundary conditions and other types of simulations. So how can they import them, and what formats, or do they create their own? What's that process look like?
Sure. So they can pull in individual voltage or current sources and use them with the circuit modeling tool. It's the standard Ansys Nexum transient solver that many users may be familiar with, but it can handle SPICE style netlist. It can handle IBIS. It's very mature, and it can handle a large range of stimuli and very complex circuit schematics to drive a representation of your actual device circuit. So the excitation may be from that circuit. It may be a measurement that you perform and bring in as ASCII data to the tool, or you can make an engineering approximation using some of the analysis tools that we have that can essentially sweep an excitation broadband across a wide range of frequencies, or bring in a source from an EMC limit curve and use that as the source. So there's a wide range of sources that are supported. And because we're using time domain simulation, bringing in a source is quite easy for users.
Mm-hmm. And that's steady state and transient signals, I would assume.
That's correct.
Yeah. Okay. Let's talk about the hardware. What do I need for a computer to run these simulations? Will I need a very special type of hardware? And do you support some of the common processing capabilities like parallel processing or high performance computing?
Yeah, the finite difference time domain technique is reasonably light on its need for resources. It certainly likes processing resources. So many engineers can do some basic EMC checks and running some simple analyses on your laptop. You probably want to scale up to an engineering workstation. They can even be towers that you can have on your desk, $5,000 to $10,000 machines that have the processing resources that you need. The technique is not that memory intensive, so you don't necessarily need 2 terabytes of RAM. You can have more modest levels of RAM. The technique scales very well across multiple cores, so you can actually use multiple cores in one machine or a cluster of multiple machines to attack massive problems. And then the last thing, you saw how graphics intensive this is. This is using 3D CAD information. So having a modern graphics card, a discrete graphics card in your laptop or your workstation, that's a good idea to have as well. But you're not going to have to go out and make a big hardware investment. It's likely going to run well on your existing high-end engineering workstation.
Oh, that's great news for the users. Well, what if I'm new and I want to get up to speed? What are the options to get training on the tool? I'm not an expert user. Maybe I don't have a lot of simulation experience. What are the options to get up to speed?
Sure. So there's several ways that you can get up to speed on using EMA3D. One way to do that is to get work with Ansys and their ACE team members that are expert on all the Ansys tools, and they can certainly help you address the problems that you want to address. But many parts of the tool are reasonably easy to use by themselves. So let me demonstrate one new feature that is the overlay documentation that we have in the tool. So anytime that I want to, when I'm using the tool, I can just click F1 and the overlay help pops up. And as I'm going through menus, the overlay help is showing me documentation for that tool. It's showing me demo videos for how to use the tool. So it can be very straightforward for new users. And many of the common simulations that you may have to do over and over on enclosures and cables can be learned even by non-electromagnetics experts. So it's not necessarily requiring a PhD with 20 years of experience to make progress. You may be designing for multiple environments, fluids, thermal, and electromagnetics, and you can use EMA3D cable, and you can answer some basic electromagnetic compatibility questions like, what's the shielding effectiveness of this enclosure as a function of frequency? What are the emissions from this cable when I have this signal applied to the cable at the same distance away from the cable where I'm going to be required to run a regulatory test? So this is really a tool for new users. It's a tool to expand who gets to come to the table for EM simulation. It's no longer just, there'll always be a role for domain experts and EMC simulation experts, but we're really opening to a wider audience that wants to answer some of these questions, and they don't have 2 decades to go become a domain expert.
Well, I like the idea of having some of the training material available right in the product. I mean, that's just super convenient as a user. My last question then, if I was interested in acquiring a license of EMA3D cable, where would I go to do that?
Sure. So these tools are available exclusively from Ansys and the Ansys channel partners. So the Ansys team can help you understand your needs, help you communicate value proposition within your company, and has a team of ACE experts to demonstrate the use of all of the Ansys products at a high level as it applies in your particular industry and company. So definitely Ansys is the right place to go to get your hands on these products.
Well, great. Well, thank you again, Tim. I appreciate your time today and sharing this expertise with us. You've provided pretty good insight for engineers who really need to ensure their designs pass electromagnetic compatibility certification. For our audience members, if you'd like to learn more about the Ansys EMA3D cable solution and how it could be applied to solve your problems, I'd recommend that you register. Tim has a workshop coming up, and the link is provided along with this podcast. In our next and our final session, we're going to look at another electromagnetic phenomenon, which is the challenge of managing electromagnetic charge and discharge events. And this includes things like charged surfaces, arcs, sparks, and even lightning strikes. Our guest for that session will be Dr. Kevin Jervis Miranda, who's the product manager for the Ansys EMA3D charge solution. Thank you again for attending today. I hope to see you again on our next session.